personally, I really like the waves module. So we have kind of like two sets of physics, right? We have like where we've been doing like a lot of motion stuff, and we've been doing that almost since like the very beginning of, part A, right? We did a lot of motion stuff. We did momentum. We were doing energy, all that kind of moving around stuff. And so now we're doing kind of like a different type. It feels like a different type of physics to me. We'll start doing waves. We'll talk about light. We'll talk about electromagnetic energy. We'll talk about lenses and mirrors and that kind of stuff. And so it's all related to waves, because light can act like a particle and a wave, but we'll kind of, for us, it'll be most helpful if we think about it as a wave. Um, and then towards the end of the semester, we'll do this little mini bit about like electricity and nuclear physics. But for the next few units, we're going to really focus on waves and light, um, and when we get into light, then we start talking about lenses and mirrors and that kind of stuff, and how light works with lenses and mirrors and things. So we need to start obviously with waves. So we have two types of waves basically. We have something called a longitudinal wave and something called a transverse wave. Let me get my pen here. Okay, so this right here is a longitudinal wave. And to me, a longitudinal wave looks like a slinky. And then a transverse wave looks more like an ocean wave. Okay, when you have a longitudinal wave, one of the reasons they call it that is because um, the motion of the wave is moving back and forth, and so is the energy. So they're moving parallel. The motion and energy are both moving back and forth like this in the horizontal direction. Okay. And then we like to label the parts of the waves. And so we call these little parts where they're kind of squished up right here. I don't know if you can kind of tell that this part of the wave is more squished than the other part. Can you tell that? Can you see that? Okay, good. We call these the compressions. Okay, so your compressions are the part where it's squished together. And I think about that, the way I remember it is it's compressed. Um, and then the other part of the wave is this part where it's real spread out. And we call this spread out part the rarefaction. And the reason, well, I don't know why they called it a rarefaction actually, but the way I remember it is I feel like the bits, of the wave, or those, if it was a spring, those bits are more rare because they're more spread out. So that's how I remember it. They're less common because they're spread out. So that's how I remember it. I don't know if that's why they called it that. Um, Scientists aren't that creative, so it probably is something to do with that. The particles are less common. Um, and then a wavelength of a wave is from one same part on the wave to the next same part of that wave. So let me kind of explain it in this picture, and then I'll explain it on the next one, and it'll make a lot more sense on the other one because we talk about a lot more with those. So let's say we're at we want to start here. Okay, this is the beginning of a compression. So we're going to go to the beginning of a compression to the beginning of the next compression, and that's going to be a wavelength. And our symbol for wavelength is this lambda and upside down y. Now, we could also do from the middle of a compression to the middle of a compression. That could also be a wavelength. We could do the middle of this rarefaction to the middle of this rarefaction. That could be a wavelength. And the reason why is because we're going from one same spot to the next same spot. So if we were to measure these with a ruler, all three of these lines, they should be basically the same amount. And you can see here in this top one, right, it's going from one black line to one black line. And this one right here was going from one black line to one black line, right? So that's basically the wavelength of the wave. Um, Now let's talk about this one, which is more probably what you've seen before if you think about waves. Um, this might be more familiar to you. We call this wave a transverse wave. Okay, now in this type of wave, the energy is going this way. It's going in one direction. It could be going the other way too. I just decided to make it go this way. But the motion of the particles are going up and down. So they're perpendicular. Okay, and so that's basically the definition of the two, is that a transverse wave, the motion is perpendicular to the energy, where in a longitudinal wave, the motion and the energy are parallel to each other. Now, we can talk about a couple different parts on this wave as well. The very, very top of the wave is called a crest. And the way I remember that is like, the very tippy top of an ocean wave is also called a crest, right? So we'll call that the crest. Um, Then we have something called the rest, or the rest position, and that's basically kind of this midpoint right here. So if all of the energy were to stop and this wave were to just kind of like, the energy would stop and the particles would lay flat, they basically lay across this line, and that's our rest. Okay, and it's basically halfway between this distance and this distance. Okay. Um, the very, very bottom of the wave is called the trough. Trying to use the same colors, so in case that helps. And then I'm going to go through a couple other terms that I didn't put on here, but I think they're important. This height right here that we looked at earlier, that's called the amplitude. And that's how far the wave moves away from the from that rest position. Okay. And then we can also talk about the wavelength. So in this one, let's say we're at the middle and we're going down and we're going up and then we're getting ready to go down again, right? So that would be a wavelength. Let's say we're at the crest, or let's try another one. Let's do the trough. We're going up, we're going down, and we're getting ready to go up again. So right here, that would be a wavelength. Let's say we're going down, right? And we're halfway. We're going down and we're halfway. Okay, that could be a wavelength. So it's 2 points on the wave, and it doesn't matter where those points are on the wave. Okay, so then we can say, okay, how many waves do we have in this picture? We've got, this one. Then we've got this one. Then we've got this one. And then we've got this half. So we've got like 3.5. Ooh, that doesn't show up very well. Okay, does that make sense? I know I just kind of made like a mess of my picture here, pointing at all these parts. Okay, cool. Okay, so these are our wave formulas. I really like these because they all fit into the triangle, right? We can do V equals D over T. We can do F is equal to 1 over T. Okay, cool. Yeah, it is a lot like physical science. And then we have a wavelength and a V over F. So you can fit all that in the triangle. Okay. All right. Okay. So now let's talk about the units. The units for frequency are hertz or seconds to the -1. You can use either one. I don't care. The units for wavelength are meters, but you may also see it in centimeters, something like that. Amplitude, that's a distance, so it would also be in meters. Wave speed is a speed, so that would be in meters per second. And period is actually a time, so it would be in seconds. But you may see a period in like minutes or something like that too. Onward. Okay, now, in this one, we want to know the wavelength, the amplitude, and the period. And then we want to know the frequency if V is equal to 15 centimeters per second. So first I'm going to do the easy stuff, right? So let me get a different color marker. So if this is a wavelength, right? 1.5 to 7.5. So we could do, oh, it's not going to show up. 7.5 minus 1.5 is what? 5? So that would be like 5 meters. Okay. Now let me pick a color that will show up on the paper, but the white, but also the black. If we wanted to do the amplitude, it would just be from that rest position to the bottom or the top, and it would just be like 4, and it would be basically like the absolute value, right? Like 4 meters. Okay. And then, okay, so we've got our wavelength, 5 meters. And so our frequency, we get a different pen. Our frequency is V equals D over T. Okay. And, well, sorry, velocity is D over T. Let me get these formulas because I don't have them memorized. We have frequency is 1 over time, and then we have wavelength is V over F. So I think that's probably going to be our best formula for now. And then the period, we'll have to use the other one. So I'm going to go in here, and I'm going to make the triangle. And we want the frequency. That's going to be F equal to V over wavelength. So that's going to be, now we have 15 centimeters and we have our wavelengths in meters. So we're going to have to move this and turn this into 0.15. Okay, so we'll have 0.15 over that wavelength of 5. And I thought I worked this one out this morning, but it looks like I didn't. And so you get, oh no, it won't write it. There you go. I'll just write it over here. Should be hertz. I'm going to cross that out so you don't think that that's like a 1-1. And then for the period, let's go 2 back. Our period is F is equals to 1 over T. So to do the period, we'll have F is equal to 1 over T. We can put this in our triangle. We're looking for the period. Okay, let me put this in my calculator. Sorry, I thought I worked this out and I don't know. I guess I got ahead of myself this morning. So that'll be 33.3 seconds. And the period is how many, like how long it takes a wave to go a certain distance, okay? And your frequency is like how many waves pass a point in a given amount of time, okay? So like this is 15 centimeters per second. Oh, look. Gosh darn it, look at me. Look at this. This was in centimeters, and I put it in meters. And so we could have skipped that whole like conversion process. Gosh darn it, that's why it's important to read your graph, right? This one's in millimeters. Oh, darn. See, teachers make mistakes too. Okay. Now let's talk about waves hitting boundaries. We used to do a really fun lab in my face-to-face class where we would have two people. I'm just going to say these two lines are the two people, and we had these super, 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 super long strings or springs. They were really, really long, and you could stand really far apart, and you could almost like one of those like double Dutch uh, jump ropes. And so they could stand really far apart, and they could one person could like flick the spring and it would send a pulse down to the other person. And then the other person could flick the spring and it would send the pulse down to them. So, but what was cool is if let's call this person one and this person two, like their heads are numbers. Um, if this person one, flicks the spring down to person two, and person two just holds it still and doesn't move, it'll hit person two and it'll bounce back to person one and it'll bounce back to person two. And it'll keep doing that until it runs out of energy. Okay. And so that's basically what waves do when they hit a boundary. They hit it and then they come back and then they come back and then they come back and then come back. Kind of like have you seen these it's called a Newton's cradle. I'm sure you've seen it with all these balls, they're like this. And you pull one back, you know, um, and it hits the others and then they come back and then they come back and hit the other one, and they just keep doing this for a while until they run out of steam. That's the same kind of thing. It's that energy that's going through those. So this is just what it can look like with two waves. This image actually makes me kind of dizzy. When two waves kind of hit each other, you can kind of see where they'll have these places where they call it constructive and destructive interference. And so let me show you what this looks like. So if we were to look at this from like a wave standpoint, this constructive and destructive interference, constructive is kind of like you're building something. So these are gonna build together. So this is kind of a weird way to think about it, but it's so let's say that both of these waves are like the same height, and we're talking about these are like the amplitude, right? So let's say this wave has an amplitude of 2, and this wave also has an amplitude of 2. If these two waves hit each other while they're both, you know, going up and, if you have your wave, like this, let's say we're looking at this part. If they both hit each other at that point, um, what will happen is they'll constructively interfere. And so they'll create this wave that's like doubly high, right? It should be like 4. Um, so this is kind of important when we talk about like earthquakes and things like that, because there are some buildings, and they've found that when they're constructing them and there's an earthquake, the height of the building and the wave can actually constructively interfere, and it can actually cause the earthquake to feel, I guess, stronger. I'm probably not explaining this very well, but it basically it's called resonant, and it makes the earthquake feel extra strong, and so it can actually cause the buildings to fall down. So there's certain buildings that are really, really high that they've built in certain areas. I want to say Dubai is one of those places, and they actually have a building that's very, very tall, and they've got something weird in there. I want to say it's like a bell, um, but they've actually put something in that building to kind of decrease the resonance with like the earth's movement and the earthquakes and things like that, so it's less likely to fall down and less likely to resonate with that earthquake, and make that earthquake wave feel extra large. So I mean, there is like a point to this, I guess, is what I'm saying. And so that's constructive interference, and that's when two things are hitting each other and they're both like going the same way, and so they're going to constructively interfere. And so they're going to get even bigger. Now, destructive interference is basically the opposite, right? And it kind of sounds like you're breaking something apart, right? So let's say we had that same wave that had like an amplitude of 2 going up, but then we had a wave that had like an amplitude. I know this is not the same size. We'll just pretend, not drawn to scale, um, of 2 going the other way. If these 2 hit each other, they'd actually be like a flat line because they'd cancel each other out. Now, let's say this one was like 3, then you'd have, a little one with like an amplitude of 1. Okay. So it just kind of depends. My students, when we would do the spring game, they would try and create constructive interference because they wanted to see it get really, really big. Um, but most of the time they ended up creating destructive interference instead.